I will talk about a transistor made entirely from metals, commonly referred to as an all-metal transistor, which I proposed and successfully fabricated it a while ago. Here you can see its design along with SAM image showing the top view of the transistor, which I fabricated in 2018. You may be familiar with the science fiction movie Terminator 2. In the film, the Terminator is a robot made entirely of metal without any semiconductors. As you know, modern electronics and computing devices are primarily built using semiconductors, especially silicon. However, replacing semiconductors with metals could offer significant advantages, such as greater tolerance to higher current and temperatures. It's fascinating to explore the idea of creating electronic and computing devices similar to those depicted in the Terminator 2, and test whether some of those futuristic concepts can be realized in the real world. Perhaps we can move away from semiconductors altogether and transition to fully metal-based electronics and computing systems. All-metal electronics and data processing offer numerous advantages beyond those depicted in Terminator 2. I would like to highlight a few additional merits. First, the fabrication process for metals is far simpler than for semiconductors. Metals in amorphous or polycrystalline structure are typically used, whereas semiconductors require high-quality single crystal. The properties of metal remain largely unaffected by amorphous or polycrystalline nature of the structure. In contrast, semiconductors rely on precise crystal periodicity to create a band gap, making high crystal quality essential for proper function. This requirement often complicates advanced nanofabrication processes for semiconductors. The simplicity of metal nanofabrication is particularly advantageous for 3D integration. When new layers of transistors are built on top of existing ones, in MOSFET transistors, maintaining the quality of upper layers is difficult because single crystal materials cannot be grown on polycrystalline layers. However, since all metal transistors are made from polycrystalline or amorphous materials, the performance does not degrade, ensuring consistent quality across multiple layers, making them ideal for 3D integration. The second merit is high endurance for high current and temperature, like shown in this movie. The metals are mostly used for their hardness and ability to withstand the large current and temperature. The third merit is a superior scaling potential, which is enhanced by two factors: lower contact resistance and lower bulk resistance. Unlike semiconductor or semiconductor-metal contacts, metal-metal contacts exhibit very low resistance, which does not limit the transistor's ability to scale down all its contacts in size. Additionally, the inherently low bulk resistance of metals allows wire diameters to be reduced without a significant increase in resistance, which allows a small size of the transistor channel. The fourth merit of all metal transistor is the faster operational speed. The speed of MOSFET transistor is restricted by the inherently low mobility of silicon, which is difficult to improve. Metal, on the other hand, have much higher conductivity, allowing all metal transistors to operate at significantly faster speeds. To start, I would like to discuss the fundamental differences between semiconductors and metals and how these differences impact the feasibility of creating key data processing elements such as bipolar and MOSFET transistors or laser diodes. Specifically, I want to explore whether this crucial components traditionally made from semiconductors could also be fabricated from metals. To do this, it is important to address several key questions about metals that are crucial for the functioning of these elements. The first question is, do metals have both electrons and holes? The answer is yes. There are both electrons and holes in metal, and in quantities much larger than those in semiconductors. A metal has nearly equal amounts of electrons and holes. Another question is, can metal be of n-type and p-type? The answer is yes. Metals can also be of either n-type or p-type. For example, metals such as copper, silver, aluminum, gold, platinum, and manganese are of p-type, while tantalum, ruthenium, chromium, zinc, tungsten are of n-type. Just like in semiconductors, the type of metals can be determined by measuring the polarity of hole voltage. Even so, metals contain nearly equal numbers of electrons and holes. Each specific metal has a slightly larger number of either holes or electrons that make them either of p or n type. The next important question is, how can negatively charged electrons and positively charged holes simultaneously coexist in metal? The answer is as follows. In metal, both electrons and holes are essentially the same particles, electrons. They are distinguished by their energy relative to their Fermi level. Electrons with energy above the Fermi energy behave as conventional negatively charged electrons, while those with energy below the Fermi level, which are described as hole, behave similar to the positively charged particles. In order to understand the electron transport in a metal, it is important to understand the physical nature of the holes. There is an incorrect classical view which considers a hole literally as a hole or a void in the ocean of electrons. It is not the correct view. For example, the hole has a spin which does not exist for the hole within this simple view. Even being incorrect, this view may be useful for understanding the transport in a semiconductor, but this representation of the hole is very confusing in understanding the transport in a metal. So what is the hole? And why are holes and electrons considered as the same particles in a metal? The reason is following. In a solid, each quantum state can be filled with a maximum of 2 electrons with opposite spins. In metals, quantum states that are occupied by only 1 electron and one place remaining empty primarily contribute to electrical transport. These states can be viewed in 2 ways, as being half full, representing an electron, or half empty, representing a hole. This is similar to the analogy to a half-full glass of wine, where one person sees it as half full and another sees it as half empty. In this interpretation, holes and electrons are not distinct particles, but rather different descriptions of the same quantum state, depending on how it's viewed. This explains why electrons and holes do not annihilate each other and can coexist in a metal. It also clarifies why holes, like electrons, have a spin. Next, I will explain why hole transport behaves similarly to the transport of positively charged particles. First, let us address a common misconception about how electrons and holes contribute to electrical current. In this incorrect view, electrical current is thought to occur because an electron physically jumps from one orbital to another, like this. And this movement in space is what generates the electron current. For hole transport, it's often wrongly believed that all states are filled except for one, and that when an electron from neighboring orbital scatters, it causes the hole to shift in the opposite direction. However, I want to strongly emphasize that this is not how current flows in either metals or semiconductors. The true mechanism is more complex and involves the collective behavior of many quantum states, where both electrons and hole transport arise from difference in energy and the distribution of particles relatively to the Fermi level. One simple reason why this jumping view is incorrect is following. The size of a conduction electron is significantly larger than the size of a single orbital. A single conduction electron overlaps with thousands and even millions of orbitals at once, making it physically impossible for the electron to jump from one orbital to another in discrete manner. Instead, its presence is spread across many orbitals simultaneously, contributing to electrical conduction as a collective phenomenon rather than through the individual jumps. The fundamental reason for the existence of electron current in both metals and semiconductors is that more conduction electrons move in one direction than in the opposite direction, like this. In reality, even in the absence of external electrical field, conduction electrons move in all directions. Under equilibrium conditions, the number of electrons moving in one direction exactly equals to number moving in the opposite direction, resulting in no net current on average. However, when an electrical field is applied, electrons moving in the direction of the field gain energy, while those moving against the field lose energy. This creates an imbalance in the energy distribution of electrons. The distribution of those moving along the field is shifted to the high energy. Consequently, the number of electrons moving in the direction of the field exceeds those moving in the opposite direction. This imbalance generates a net electron current. As shown in the figure, with an applied voltage, there are 3 electrons moving to the left and 2 electrons moving to the right, creating a net electron current to the left. I want to emphasize this important point once more. Current flows in both semiconductors and metals because there is an imbalance in the number of electrons moving in opposite directions. This imbalance is caused by difference in the energy distribution of electrons moving forward versus those moving backward. Therefore, the direction of the current flow is determined by the shape of the electron energy distribution. In this example, the distribution of electrons in the conduction and valence bands of semiconductor is schematically illustrated. The blue area shows the number of electrons moving forward, while the green area shows the electrons moving backward. When an electrical field is applied, the energy distribution of conduction band electrons shifts, causing more electrons to move forward than backward. This results in a current flowing in the direction of the field, effectively behaving like a current of negatively charged particles. Conversely, in the case of valence band holes, the energy distribution shifted so that more electrons are moving backwards and forward. As a result, the current flows opposite to the field, effectively behaving like a current of positively charged particles or holes. This means that electrons can behave either as negatively charged particles or as positively charged particles, depending on the shape of the energy distribution. This graph illustrates the energy distribution of states occupied by single electrons, like this, in metal under the influence of an electrical field. The green line represents the distribution in the absence of a field, while the red and blue lines show the distribution for forward moving and backward moving electrons respectively. As you can see, for electron with energy higher than the Fermi level, this here, the red line is higher than the blue line, indicating that more electrons are moving forward, behaving as negatively charged particles. In contrast, for electrons with energy lower than the Fermi level, these electrons, the red line is lower than blue line, meaning more electrons are moving backward, making them behave like positively charged particles or holes. Thus, electrons with slightly different energies can behave either as positive or negative charge carriers, depending on the energy distribution relative to the Fermi level. Electron transport is often conventionally visualized using distribution sphere, where the length of a vector from the axis center to its surface corresponds to the number of electrons moving in that direction, from this to this. The direction in which the spheres shift under the electrical field determines whether the carrier behaves as electrons, like this, or as holes, like this. This concludes part 1. In the next part, I will explore the potential for fabricating various electronic and data processing devices, such as laser emitting diode, field effect transistor, and bipolar transistor, using only metals without relying on semiconductors.